So we have five speakers to come. The first one is Dr. Khaled Alshehri. Dr. Alshehri received his bachelor degree, Bachelor of Science on Control and Instrumentation from KFUPM. And then he went to the U.S., to University of Illinois at Urbana-Champaign, where he got his master's and PhD in areas of computer science and electrical engineering. He is currently the AI advisor and the energy subject matter expert at Saudi Data and AI Authority, SDAIA, just to come show how much interest the government has in this topic here in Saudi Arabia. Dr. Alshehri also served as an assistant professor at KFUPM and R&D engineering in the U.S. Please come to the floor. And could you start the presentation here? Yeah. If you could stay in this area so the camera can see you.
Sounds good.
Thank you.
This is the clicker. Thank you very much, Bassam. I'm very happy to be here. So today I'm going to switch gears a little bit and talk about power systems. We haven't had much about power systems yesterday. So I'll talk about some AI applications for smart grid operations and economics. Before we start, what is a smart grid? Can anyone share some thoughts about that? Smart grid. What is a smart grid? Yes.
Just depending on the demand.
Okay, so how is that different from a traditional, let's say, power grid?
Takes some measurements of the demand and then, it does it automatically based on the user instead of manually checking the user.
So you have the demand proactiveness in the system. So one of the main elements of a smart grid is having this, what is called demand side management, where you have, instead of having a one-way power delivery, you have a proactive demand component. And that proactiveness brings a lot of interesting questions into the picture, and it changes a lot of the assumptions too, which makes this area pretty much interesting for a lot of R&D development. So as an outline, I'll give a bit of a background, and I'll talk about some unique characteristics of power systems that makes them uniquely complex. And I'll talk about some selected AI applications. This is a mixed audience, so we have academics and we have practitioners. So I'll talk about some theoretical contributions in addition to some practical aspects. And then I'll talk about key factors to enable successful deployment of AI-based solutions. And we'll have an open discussion. So here we have on the left a traditional power grid. So basically, power system engineers, they have mastered the art of one-way delivery for the last century. So you have generation, and then you have transmission and distribution, and then you have the customers at the end. So you have these passive customers, and power system engineers have mastered the art of meeting that demand continuously and instantaneously. But with the smart grid, what you have is this architecture is being questioned. I mean, you still have the same major components, but there is a major shift in the demand side. Customers are now becoming more and more proactive, and that goes to large-scale customers, and it also includes end customers or end consumers of electricity, who are now, some of them call them prosumers, people who want to sell back to the grid. So you have electric vehicles feeding back to the grid. You might have solar panels feeding back to the grid. So you have all of these questions that question some fundamental assumptions or some ways that the power system has always been operating, but now they are changing. And also you have renewables on the rise, and you have all of these interesting changes. So this is another way to look at it. We have generation, we have transmission and distribution, and we have the demand side. So now the demand side is feeding back to the grid, and also you have the advanced metering infrastructure pretty much everywhere, and that generates large amounts of data. So what makes power systems uniquely complex compared to, let's say, other kinds of engineering systems? So you need to have instantaneous supply and demand balance. This is pretty much unique and critical. Electricity is an unstorable commodity. And because of that unstorability, that creates a lot of complexity. So if I switch on the light right now, that light is freshly made maybe 100 kilometers from here in a fraction of a second. This is done in a fraction of the second. This is not the case for other kinds of engineering operations. So this is a unique aspect, but with the rise of a smart grid, with the rise of renewables, and with the end customers wanting to become more and more proactive, some fundamental assumptions, some fundamental engineering assumptions need to be revisited. I'll highlight two main assumptions. The first assumption is the inelasticity of the demand, meaning that customers are passive. Now they're becoming more proactive. So if I look at it from, let's say, a stochastic optimization problem, then you have a nominal demand being replaced by a highly stochastic variable. So that changes a lot of things. And you have also the temporal dependencies added to that. Another level of complexity comes from the generation side. Instead of having, now, if I have gas turbines or fossil fuel-based generation, then I know with how much, let's say, fossil fuel, how much power I can generate, and I can plan for it pretty much reliably for the next day. If that's gone and it's replaced by renewable generation, then I introduced stochasticity and uncertainty into the system. And that complicates the other end of the spectrum. So you have the supply side being changed, and you have the demand side being changed. So you have these critical fundamental assumptions being questioned. And power system engineers have mastered the art of running the system reliably, but these assumptions were not there. Or let's say these assumptions were there. They always have, the usual assumption is that you have nominal demand pretty much that can be forecasted accurately, just weather dependent, and you have controllable supply. So this is just to highlight the changes. So we have, for example, sample wind generation on the left and sample solar generation on the right. So we have uncertainty. So these are not always easy to forecast. You have intermittency. So you have some unpredictable ramps. And that causes an issue because, remember, we're talking about instantaneous supply-demand balance. And we have non-dispatchability, meaning non-controllability. So I took this from the California Independent System Operator website. This is Tuesday last week. And here is a change, an interesting change to observe. So the green line here represents the system demand. This is the energy consumption in the state of California. The purple line represents the net demand. This is the energy consumption after the solar. And most of this, I believe, is from the distribution side. This is rooftop solar. So in summer days, the green line has a peak. And usually power system engineers try to minimize the peak, what's called the peak to average ratio. That was an issue. That was something to keep in mind. But now, after introducing the solar at large scale, I think this is exceeding 50%. You have this dip. So we solved the problem and created another problem. This is pretty much what's happening here, power systems. So one issue here is that you have to quickly ramp up the generation, which means the following. It means you have to use the most expensive generators because you have different kinds of generators, and these generators work in different operating hours. So in day ahead, usually system operators in day ahead, they plan for the generation, and you have different generations at different, let's say, time scales. So the cheaper ones are usually slower to ramp up or ramp down. But now you have to ramp up very quickly within 3 hours because of the sunset. And this is the most expensive part. So this is just to highlight the added complexity when we introduce renewables. This is from the supply side. Add to it, for example, demand changes in the behavior. So and there has been a lot of interest in this area. I mean, this is actually back in 2018. So this has been going on for a couple of years, or maybe more. Actually, the smart grid term, I think it was introduced in 2003, and that with an initiative that funded a lot of research in this area. So here, DOE, the Department of Energy in the US, was funding generously in the area of data, AI, and machine learning. This is an example. Also, another change that is going on is that because of this customer proactiveness and because of the recent technologies, by recent I mean the last few decades compared to the last century, you have now the concept of a microgrid, where you have a smaller part of the grid that can operate independently and feed into the system and can isolate at the same time, where you have some nanogrids. This is an example in Chicago. In the Chicago area. This work was done by ComEd, Commonwealth Edison, the utility in Illinois. So basically, and this is at IIT, Illinois Institute of Technology's campus. So they had this experiment they called IIT microgrid. I mean, there are many experiments like this. This is just to highlight an example. So where you have some academic buildings, some controllable generation, police station, and this can isolate and it can connect to the grid. So it can take from the grid and it can also feed into the grid. So this is an interesting experiment, and there are many like this. So what I'm trying to say is the following. Now, 20 years ago, there was a lot of interest in this area, and it's still going on. Now we see some of these examples happening. So now this is becoming a reality. And having this conference is part of this reality, right? Because we have people talking together and also collaborating in this area. So you have the decision-making aspect with AI, and you have IoT generating massive amounts of data. So this calls for the use of AI and machine learning because there are infinitely many applications in this area. The power system, it's a large system, it's complicated, you have massive amounts of data, and it's highly nonlinear system, and there is a lot to do in power system. Pretty much any tool you have, from AI, controls, optimization, has many applications in that domain. So now we'll talk about some selected applications. So I'll try to strike a balance between theory and practice here. So just some examples. Obviously, we have load prediction. You could have renewable generation forecasting. You could have power flow and sensor measurements optimization. You can have adversarial tampering. This goes into cybersecurity. You can have virtual trading, which has connections to economics because in many countries around the world, the power system is deregulated. For example, in the US, there are 9 system operators. Each of them has hundreds of market participants, and each market participant could be a generation company or it could be a distribution utility. So it's being sold daily and bought daily, but that is usually at a large scale. Now, a major shift into that paradigm is having that happening at the small scale, meaning instead of having thousands of market participants, you would have millions of market participants. So that changes a lot of things down the line. You have market monitoring, of course, and you have modeling end consumer behavior, these proactive consumers, and many other applications. So maybe this picture by Irina's report is kind of categorizes 6 main themes. So we have the generation, we have maintaining grid stability and reliability. This goes into the daily operations, and you have demand forecasting and efficient demand side management. This is when people schedule their consumption. So demand-side management is a term that has been used in power systems. So the simplest form of that is having social awareness programs. The most advanced form of that is where you leverage AI fully. This is when you have automated decision-making at the customer side. This is when you have your electric vehicles being automatically adjusting its consumption based on your preferences in real time, in coordination with the grid operator. And you have optimized energy storage and operation that goes across, and you have optimized market design and operation. So we'll start with optimized market design, and we'll talk about a theoretical work that we've been working on. So one question you have here now, you have a power system with a power system market with thousands of participants, and now you want to introduce millions of participants to sell back to the grid. So what is the right, let's say, pricing policy? How do you model that interaction? Do you ask people to sell back to the grid at a lower price than their billing rate? Or do you introduce, for example, a two-part tariff where you ask them to pay a connection fee plus they pay a marginal, they get paid at a marginal rate? So this is a policy, and also you have to consider different aspects. You have to consider the overall market efficiency, or let's say the total system cost of meeting the power system demand. You have to consider some aspects related to regulation. You have to consider also the companies that are being participants here, because I cannot sell back to the transmission grid directly. There are distribution lines in between that is, let's say, operated by certain companies, and some of these are profit-seeking entities. So what is the right balance between ensuring that they can flourish, but at the same time introducing this system supply, let's say, at the distribution lines, while satisfying everyone, let's say, while being fair to everyone. So this goes into economic efficiency, and we have introduced a game theoretic framework to address that. So here we have a sketch. So we have a wholesale market. This is, let's say, a country level, or let's say half-country level kind of operation. You have prosumers. These are people like us who might have rooftop solar or EVs who want to sell back to the grid, but we do not have access to the transmission lines, and we shouldn't. And you have here entities in between who might do price arbitrage, meaning benefiting from the price difference between the market price and what they offer to us to sell back. So this is assuming decision making at different levels. That this is today maybe not realistic, but this is going to happen down the road. And here we're trying to answer at least some policy questions. So you could have a price offer sent to prosumers. You can receive a price. The utility can tell you, for example, you can sell back at this certain rate, and you choose your capacity. And based on that equilibrium of the game, we use a game theoretic technique here. We have some market outcome, because at the end, this will affect the overall market operation. On the right, we have the benchmark, or let's say some sort of an ideal model where you have this direct participation from prosumers to the market. This is not realistic, but this is the economic benchmark that represent an efficient allocation of energy. So this price row could be one-dimensional, meaning that it's just a rate you sell back at, or it could be two-dimensional, meaning that you have a connection charge plus you get paid at another rate. And what we have found out that if you do two-part pricing, the equilibrium of the left gives you an overall system cost that is exactly equal to the equilibrium on the right, while ensuring the rationality of assumption of every market participant here. We can talk about the details offline, but this is one major highlight here. You could do also, back to the curve that I showed earlier, the duck curve. It's called the duck curve. We could do some, this is a work of my students back in KPPM. You could do some sort of, for example, you can forecast the solar generation, and based on that forecast, you can do some sort of model predictive control to shrink the gap between the two lines. So now we're done with the academic part. If we can go to the practical aspect here. And I'll pick this example. This is power loss prediction. So as I mentioned, the power system is quite complex, and it's a highly nonlinear system. It's non-convex, and it has losses because when you generate the power, not all of it gets delivered to the, let's say, to the nodes. So you have maybe supply nodes feeding the demand nodes, and not all of that power is transmitted. Some of this is lost due to many physical factors. So one important application where you could use machine learning, and this is the work that we're doing right now, where we could build an AI model, we could build a machine learning model that can forecast the power losses. So the input data could be historical losses and historical power flow. It could be some other operational data. It could be weather events, and you can have line features. And once you do that, I mean, you can have a variety of problems here to address. You can do forecasting, you do regression to forecast the power loss. And based on that power loss, that information can also optimize the operation. Right? You could do optimal power flow. You could also investigate the root cause of these losses, and that can also help in terms of maintenance and other reliability-related aspects. Once you deploy this in real time, you cannot rely on historical weather, obviously, so you need to have reliable forecasted weather to give you reliable power loss predictions. Another example here would be, for example, fault diagnosis in transmission lines. A third example, more related to computer vision, would be asset identification and mapping. And there are many examples that we can think of. Actually, some of the examples yesterday were from oil and gas industry, and pretty much a lot of that is still applicable to power systems. Now, we talked about the customer proactiveness, and there is a major element here, which is the use of smart meters. Passive consumers of electricity, now they are becoming more proactive, and luckily in this country, pretty much smart meters are everywhere. And because smart meters are everywhere, you're generating massive amounts of data from the demand side. This data could be leveraged in many ways. Again, you can go to full-fledged automation of customer proactiveness, automated decision-making, but there are things that could be done before we do that. You could do bill prediction, you could do appliance consumption analytics. For example, from the aggregate demand profile, there are machine learning techniques that could tell you how much of that demand, where is that demand being consumed? How much of that is going into, for example, air conditioning or lighting or cooking or whatnot. There are other applications related to carbon footprint, feedback to customers. If you allow peer-to-peer trading, obviously you need smart meters too. So we have a few minutes, maybe we can talk about deployment. So usually, when you talk to machine learning researchers, usually you see a focus on accuracy and maybe more simulation-based metrics. When you talk to software engineers, they will think about more on, let's say, more into the other aspects of deployment. But there is an area in between where you have MLOps, you need to ensure people communicating to each other so that you have successful deployment of these AI solutions. You can have a good model, but that is pretty much hard to deploy. So there are factors that enable successful deployment. So my message here is to keep in mind the big picture. So you have legacy systems like the power system that has been going on for the last century, and you have massive amounts of data, and these systems are state of the art. So we have to keep in mind that you have a lot of instrumentation, a lot of sensors, and this data is being stored somewhere, and you need to know how to, okay, 3 minutes. You need to know how to, for example, which data sets are most suitable and which data sets that can lead to successful AI deployment or model development. Because if you look at it purely from a research perspective, you might have a gap there. So this is, so for example, the elements that you can keep in mind is that, for example, DevOps, MLOps, and this is quite critical because at the end of the day, it's not about having a good model at the end of the day. At the end of the day, you want to deploy that in real time. So you have to consider the pipeline, you have to consider integration, you have to consider all of these elements. You have to consider dependencies in the software development cycle. I mean, here's from Irina's report, for example, they mentioned an interesting checklist that has technical requirements, policies needed, regulatory requirements, and some aspects related to stakeholder engagement. So that's pretty much it from my side. Thank you very much.
Thank you, Dr. Khaled, for this. The floor is open for questions. Please wait for the microphone. Thank you for this overview of all the opportunities in power network and using AI for that, both in the demand and the supply side. Sumitra?
Thank you so much for this insightful and very important talk. I always had this question that when we combine renewables with the traditional power generation, for example, gas turbines, and so how much of the percentage of renewable is possible? There are physics-based limitations. For example, as far as I know, there cannot be 100% renewable in a power supply because of requirements of synchronous power. So could you please comment on that? Like, how do you consider those issues?
How much renewable is possible is pretty much tricky because it pretty much depends on the reliability requirements, on the checks and balances of the system. But the main message here is that with renewables, you introduce stochasticity into the system. So there is a limit where you can manage stochasticity, but at the end of the day, you have some, for example, reliability standards that you don't want to violate. And that is pretty much system dependent. Some systems are run into what's called N-1, meaning that it will operate normally in the absence of one major component. Some systems have a higher standard of N-2, meaning it will operate normally at the absence of two major components. So you have a variation here, but I think successfully you could have a large percentage, but there is a cost associated to that you need to also be aware of the added complexity into the system operation. So I would go with maybe 30 to I don't know, 60. That's my humble opinion, 30 to 60%, but it's still quite high sometimes.
Yeah, there's evidence around the world of much higher than that. But Shri, quickly, I think the US done some modeling of its network, and it could add another 30% while maintaining the stability of voltage and frequency. But Shri, please.
Thank you very
California
much.
is planning to go for 100% at some point. Now they're operating, I think, at more than...
Yeah, it's all about storage at the end and synchronous power. I think that's the key component. Please, Shri.
Thank you very much. It's a very interesting talk for the time. So I just wonder, like, when we became smarter, means like the smarter grid, what I understand is the end user is supposed to be smarter as well, meaning like in terms of like bidding for the power, like on the price. Are we smart enough, like just our end user community is fully aware, and do we need to do anything to make them smarter? I mean, just I wanted to understand you comment on that, your thoughts
Okay,
on that.
so things like that take time. So you could, I mean, if you look at the literature, you will see papers where you have full consumer proactiveness, but that might be a bit far from reality everywhere. Like maybe in some places, it depends on where you are. But I think this is going to happen gradually, and it started to happen. For example, now with the presence of smart meters, you have a chance to give insights to the customer. With time, you have a chance to maybe install some hardware to allow them to be more proactive. Now with electric vehicles, maybe customer wanting to sell back to the grid, rooftop solar wanting to sell back to the grid. So I think that customer proactiveness is an interesting journey. This is why I try to balance theory and practice here, because I think it's an ongoing opportunity but with time, obviously, you will have more customer proactiveness and you will learn your own preferences with AI too.
Please, we have to move on. Please join with me in thanking Dr. Khaled.
Thank you very much.